Hello, my name is David, and I'll be giving you a presentation covering some simple commands in SageMath as it pertains to coloring. Let's create a graph with a vertex that is adjacent to 8 other vertices. We'll call the graph G1 and place vertex 0 in the center. To do this, name the graph with the equal sign, use the graph function, and state that vertices 1 through 8 are adjacent to 0. We then print the graph to the screen. So here you have the name of the graph is G1, it equals the function graph. Vertex is 0 is adjacent to 1, 2, 3, 4, 5, 6, 7, and 8. No other vertices are adjacent to one another. So we'll now print G1 to see what it looks like. Okay. From inspection, it's clear that a proper coloring could be achieved with just two colors, with the vertex in the center being one color and all of the vertices on the outside a different color. So here's how we could draw it in SageMath, where we've assigned the color red to the vertex 0, and then we've assigned the color blue to the vertices 1 through 8. And there we have it. Proper coloring is achieved. But what if determining proper coloring isn't easily apparent like this example? Is there a SageMath command available? Yes, we first have to import the vertex coloring command, which is this command here, from sage.graphs.graph_coloring, import vertex coloring. So we'll run that. Next, we'll run the command vertex_coloring and the name of the graph. And what it gives us, it says that vertex 0 needs to be one color, and then vertices 1 through 8 could be a separate color, meaning two colors are required for proper coloring of graph G1. So we can see that the 0 being the color red and the vertices 1 through 8 being the color blue is exactly what I came up with before by inspection. And so we'll just reprint that to the screen to show you what it looks like. All right, so let's try an example of a cycle graph. So we'll call it G2, and we'll do a cycle graph with 15 vertices, and we'll print G2 to the screen to see what it looks like. Okay, so we just have a cycle graph, and then we ask SageMath how many colors would it take to do a proper coloring. And it tells us that vertices 14, 12, 10, 8, 6, 4, and 2 need to be one color, and then this separate set of square brackets is a second color, and then a third color would be needed for vertex 0. So again, I'll use the name of the graph dot show, use vertex colors equal, and I will assign red to this first set, blue to the second set, and green to the third set just to see how it looks. And there we have it. Proper coloring where no reds are adjacent, no blues are adjacent, and no greens are adjacent. Since there's only one green, that makes a whole lot of sense. So to reinforce this concept, here's a slightly more complicated example. We'll call it graph G3. And what we have is a graph on 4 vertices. Okay, now we'll check to see how many colors are needed. And SageMath says that we'll need 3 colors such that vertex 2 is one color that is different from vertex 1, which is different from vertex 3 and 0, which are the same color. So we can cut and paste this information into our plot and see what it would look like. And again, we have a proper coloring because the greens are not adjacent to each other, nor is a red adjacent to any red, and blue is not adjacent to any blue. Okay, so now we'll move on to a little more complicated with G4. So from inspection, we can see that this is going to be a little more challenging. So using SageMath, using the vertex_coloring, we can run it and find very quickly that only 3 colors are needed, such that vertex 4, 5, 3, and 1, and vertex 2 are different colors, and the vertices 6 and 0 are a third color. So we'll run that. And now it's much easier to see how they we have achieved a proper coloring. So we'll move on to graph number 5, a complete graph. Ask how many colors are needed. And it says that we need a total of 5 colors. So again, we'll cut and paste. And a proper coloring has been achieved. Okay, so now with this 6th example, the Moser spindle is a planar graph. It's often used to demonstrate the fact that 4 colors are necessary for coloring planar graphs. So we'll show it below. I just named it Moser. And so with this planar graph, as we should know from class, it's going to require a total of 4 colorings, such that vertices 3 and 6 are one color, vertices 5 and 2 are a separate color, and vertices 4 and 1 are a third color, and vertex 0 is a fourth color. So we can run that, and there we have it, a planar graph that demonstrates the 4 colors that are needed. So what about the United States? Is that really colorable with just 4 colors? Well, it turns out SageMath has a map of the United States saved in the system. So we'll just call that using graphs.usa map parentheses, and we'll plot it. And that's a bit messy, but what we can do is ask vertex coloring. How many colors would it take to color in the United States for a minimum amount of colors? Sure enough, one set of brackets for these states. So that's 1 color, 2 colors, 3 colors, and 4 colorings. Which kind of begs the question, can every planar graph be colored with just 4 colors? Well, it turns out that a biologist named Aubrey D. Gray found an example of a planar graph that takes at least 5 colors. He did this by combining the Moser spindle to have a total of 1,581 vertices. This breakthrough occurred in 2018, a full 68 years from the original proposal by Hugo Hadweger and Edward Nelson, who thought the lower bound was 4. But since de Gray's discovery, a 633 vertice planar graph has been shown to require 5 colors as well. So I hope you found this to be informational, and thank you for joining me today. Hopefully you'll see the beauty of SageMath in determining minimum amount of colors needed for your future graphs.